Hello, wonderful people. We're going to do section 7 and 8 together because this tells us what is light. Now, I'm sure we talked about light as photons back in mechanics when we were talking about light. And I think I even talked briefly about how light is both a particle and a wave. And it depends on how you look at it as to what you see, which is very mysterious and weird and confusing. And that leads into quantum physics. But we ran out of time and we're not going to cover that chapter. So, but I still want you to know what light is, and this is going to answer that question. So first we have to talk about the induction of electric and magnetic fields. A magnetic field is created in any region of space in which an electric field is changing with time. So, do you remember with the transformers? We didn't the magnetic field caused as the magnetic field changed and crossed the coil of wire, that induced an electric current in the secondary coil of wire. So it's very similar to that. What we're saying now is going a step further. If you have an electric field that's changing with time, so if the electric field is getting bigger or smaller or just moving, then you get a magnetic field. So, electromagnetic induction has been discussed in terms of the production of voltages and currents. But the more fundamental way to look at it is in terms of the induction of electric fields. Because the electric field is, after all, what pushes the electrons around, and that push is what makes voltage. And then once the current is pushed through something, then that makes the current. So it starts with the field. You have to have the electric field to push the voltage and the currents around. So induction takes place whether or not a conducting wire or any material medium is present. And by medium, I mean something that the charges would flow through. Faraday's law states that an electric field is created in any region of space in which a magnetic field is changing with time. And that is the fundamental point of it right there. Just checking where I'm at. The magnitude, how big, of the magnitude of the created electric field is proportional to the rate at which the magnetic field changes. So if the magnetic field changes a lot, then you get a really big electric field. If it's really small, you still get an electric field. You just get a small one. And the direction of the created electric field is at right angles to the changing magnetic field, which is hard to imagine. We have a picture later. Now, if you have an electric charge, and if it happens to be present where the electric field is created, this charge will experience a force. And that's what we've been talking about. That force is what pushes the currents around. For a charge in a wire, this force could cause it to flow as a current or to push the wire to a side. Forget about the second bullet. And here we go. This is where we take this step. There's a second effect, which is the counterpart to Faraday's law. So if an electric field happens to be present when the electric field is created, it experiences a force. But there's still a second effect. It's just like Faraday's law, except that the roles of electric and magnetic fields are interchanged. A magnetic field is created in any region of space in which an electric field is changing with time. So we started here. An electric field is created in any region of space in which a magnetic field is changing with time. And now we're saying a magnetic field is created in any region of space in which an electric field is changing with time. The magnitude is proportional to the rate of the change, and the direction is at right angles. So If you have an electric field and it's changing, that makes a magnetic field. And then a magnetic field is created when any region of space in which an electric field is changing with time. Oops. So if the electric field is changing, that makes a magnetic field. And then when the magnetic field is changing, that creates an electric field. And when an electric field is changing, a magnetic field is created. So how can an electric field create a magnetic field? If it's in motion. An electric field in motion creates a magnetic field. And finally, we get to the point of it all. An electromagnetic wave is composed of an oscillating, changing, electric and magnetic field that regenerate each other. So here's a stick with a bunch of charge on it. Shake the end of a stick back and forth in still water. Sorry, it started with a different example. Shake the end of a stick back and forth in still water, and you will produce waves on the water surface. Similarly, shake a charged rod back and forth in empty space, and you will produce an electromagnetic wave in space. How? The shaking charge can be considered an electric current. As this is moving back and forth, you have a moving electric charge. And a magnetic field surrounds an electric current, a moving electric charge. A changing magnetic field surrounds a changing electric current. A changing magnetic field creates a changing electric field. The changing electric field creates a changing magnetic field. And then you go back to the beginning. And this is what it looks like. You start off by moving the electric field. So this gets bigger, and then that creates a magnetic field, and that gets bigger. And then when this, you know what, I'm not going to try to explain this because this is not, I'm going to wait for you to see it in the lab. That will just be much better than me trying to explain this because it's hard to see until you just see it in motion. So, I couldn't find it in a quick one online, so I'll just save it for the lab. For electromagnetic radiation, there is only one speed, the speed of light. No matter what the frequency or wavelength or intensity of the radiation, it's always traveling at the speed of light. The changing electric field induces a magnetic field. The changing magnetic field acts back to induce a new electric field. About the speed of light, 300,000 kilometers per second. And it was Maxwell that discovered all this. This includes radio waves, all the different kinds of waves that are out there. X-ray, gamma ray, microwaves. So what makes up an electromagnetic wave? There it is. A changing electric field makes the magnetic field. A changing magnetic field makes the electric field. And back and forth and back and forth. Okay.